All right, welcome everybody. This is Fred Schenkelberg, and welcome to today's webinar on just an overview or a high-level discussion about physics of failure. And I'm sure you've heard of this, the POF. There's a couple of conferences out there, and there's much discussion about what it is and what it isn't, and how to use it, and best practices, and all kinds of other things. And I'm going to cover a couple pieces of this and try to demystify it a little bit, and encourage you to use these tools as you work on your various aspects of your products or systems in order to understand and or improve its reliability performance. And so hopefully that all will make sense as we get through this. So we deal with failures. As a friend of mine once said, reliability professionals come to the team from a failure perspective. And we are constantly thinking about, exploring, understanding, and anticipating failures. The product doesn't work as it expects to work. And I often joke that it makes it difficult to get on an airplane knowing what we know. Although I should be more concerned about getting in a car and going down the freeway here than I should be about getting on an airplane, thinking about the just straight probabilities. Yet that's the way we're wired. That's what we do, from early FMEA work all the way through to detailed field failure analysis and root cause analysis. We tend to focus on what doesn't work. Now, our compatriots, the people that we often work with, either in the factory or in the product development team, are looking at successes. How can I make this work? And so part of what we do is dealing with the failures in order to make it work long enough or well enough over some duration. And so a little bit of insight here is that's the way we approach what we do as reliability professionals. Yet we have a bevy of tools at our disposal to deal with this. Now, one of them is root cause analysis. When something fails, we often are part of a team that looks at, well, what went wrong? Was it a poor material? Did it age incorrectly? Did a rivet fail? Did a bird strike into the engine compartment? What was it? Now, oftentimes we're dealing with things that have failed, and sometimes catastrophically. They burn or deform or melt or are destroyed in large effect. And we're left with basically clues as to what happened. So it makes it very, very difficult sometimes to pinpoint exactly what was the underlying cause. Now, the other note I wanted to have on this slide is that there's often two parts to this. And then a good failure analysis or root cause analysis will cover both of these aspects. One of them is, what's the physics and chemistry or the fundamental item that initiated and or led to the ultimate failure that was experienced? What got it going? And so for example, if a flange wasn't formed correctly and it had a crack in it, and that crack then was able to propagate in its use environment and separate, that would be that manufacturing process error that led to that embrittlement or that cracking would be our root cause. Now, you could argue you could go further down to material sciences and into the infrastructure of that metal lattice, or you could do it at various levels, but it's usually to the point where you can take action. And that's the key part of the going to root cause, is the part where you understand it well enough that you can take action to remedy it, whether through design or a process change. The other aspect of root cause analysis, and I know I spent way more time on this in another webinar that was more focused just at root cause, is usually errors and mistakes, especially in designs of equipment, are due to a decision, not having appropriate information or a the appropriate interpretation of that information. And so in a perfect world, we'd have all the best information in order to make the right decision every single time. We chose to size that flange with particular dimensions in order to support a particular weight, but we may not have known that the amount of vibration would amplify that load, and that's what led it to fail. So part of what we do in root cause analysis is try to understand how to inform those decisions along the way. Now that's a trickier part, right? We should have known something earlier in the process in order to avoid a failure. There's a lot of information we potentially could know, but yet we got to narrow that down a little bit. So keep that in mind. I'm going to bring this topic back up a couple more times. And then a third part that gets involved here, and I use the term mathematics instead of statistics. And it's splitting hairs, I think, to a large extent, because part of what we do with physics of failure is model. And what I mean by modeling is not building a small paper airplane, it's building a mathematical representation of that airfoil, for example, or the material properties of that aircraft, or some other aspect that's salient to what we're interested in and what's going to fail. And sometimes it involves simulation tools, sometimes it's a simple formula, sometimes it's deterministic, and there's no statistics involved, and other times it's purely observation, and we're using statistics to deal with the variability of, say, material properties. We got to do the math, and that's the part that I think trips up most people when they get into physics of failure. Now, over the years, I've asked, I don't know, thousands of people in different seminars and workshops and classes and so on, of how many of you enjoyed your statistics class in undergraduate school. And usually there's one or two folks out of 100 people that raise their hand and admit that, yeah, they enjoyed that. I also have asked on occasion, how many of you do calculus or equivalent level of math on a daily basis? And there's nobody. On a monthly basis, maybe one or two people. Now, a lot of what we do as engineers is based in math, and you got to get comfortable with that and pull those books out and pull those tools out and do the math. And physics of failure will bring that to the front big time. So we got to understand what we're doing. We got to be able to do the modeling and understand those models much more so than basic arithmetic. And so we'll highlight some of those differences as we go. All right, so here's a question for you. And I know I've mentioned this set of stresses on occasion. 85% relative humidity and 85 degrees Celsius is a very, very common set of stresses to apply to a wide range of products through standards. And so it's a common stress for environmental testing for a huge range of different products. So if you do that to your product, if you put it in a high humidity, high heat chamber for some amount of time, how do you interpret that? Is there a model to interpret that to something useful? Because, so a couple of questions in here for you, but how do you deal with this? How do you interpret this? Okay, David's mentioning the PEC model, and it's a formula that relates relative humidity levels for use and testing conditions and temperatures between use and testing conditions. And you're right, it's for encapsulated devices. And it's really looking at, is it sealed well enough so that we don't get contamination leaking into the active element of that encapsulated component. Now this was started way back at Motorola years and years ago, I think 70s and 80s. And PEC accumulated a bunch of studies that looked at testing conditions and then how did those devices survive in more applied or actual conditions, use conditions, and created a whole series of correlations. And that's where those model configurations come up. And I do have a slide on this model near the end of the presentation. Yet it's critical that, and where I run into problems with this, and I've mentioned it, I think, numerous times in these webinars, is that the way David mentioned this is that it's for encapsulated devices. Now, it's further refined, it's for particular types of overmoldings and lead frames, right? If you really get into the details of where the data came from, it's pretty specific as where it applies. And that's a key aspect of physics of failure models, is that we are focusing in on the failure mechanism, the actual physics and chemistry of what's failing, and how we mathematically describe that failure, time to failure phenomena over time. And that allows us then to make adjustments and to understand different options and so on. We'll talk about how to use this in a little while. But if you use 8585 stress on something that's not a electronic overmolded or encapsulated component, PEC's model doesn't apply. It really doesn't help you one way or the other. It's just doesn't help. It doesn't give you any useful information. Unfortunately, it will give you a number at the end of the day. You can put in the conditions and numbers and use conditions and test conditions, and it will spit out a number 42, for example. Yet it is irrelevant if your failure mechanism is different than what this model applies to. And so that's where I see this being misused so many times, is be very, very cautious about which model you apply and make sure you understand the connection to what you're interested in. Let's talk a little bit about physics of failure in a little bit more detail. There's tons of models, right? Now, as George Block said, all models are wrong. But it begs the question of, why do we use models, right? And it's because the world is really, really complex, and there's a lot going on, and there's more than we have the capacity to fully understand and create a deterministic representation of it. So we use models to simplify the interaction between stresses and time to failure, for example, for what we're usually interested in, so that we can make estimates, we can make comparisons, we can influence design criteria, and so on. A very, very simple model is that a circuit board, in general, an FR4 multi-layer fiberglass circuit board that we use day in and day out in so many products, can typically dissipate about 1 watt per square inch. And it's just a rough guideline. And when you have a series of components or number of elements on your system that will generate more heat than that, then we need to think about cooling. And so that's a very, very basic model of looking at a simple system. How much wattage am I losing or dissipating on the components on our circuit board? And do I need to make a decision to do something different? Now, we can also do much more sophisticated thermal simulation models and looking at heat dissipation and ramp rates and flow rates, and modeling both conduction and radiation and all the other ways heat can move, and we get these beautiful maps of heat profiles on a circuit board. Yet it just gives us another level of detail, another refined look at what we're doing. One is just a simple guideline that's based on some basic fundamental observations in science, and the other one is a very detailed, much more refined in resolution part, using a range of different mathematical formulas that talk about how heat moves, and using computer modeling and simulation tools in order to get the results. Not that one is wrong or right or better or worse, it's just they're different tools, right? Sometimes I need a small jeweler's hammer and sometimes I need a sledgehammer. And pick the right tool is the real key here. Now, physics of failure models are really just those formulas that translate our use conditions into our stress conditions and back into time to failure. By and large is what we're interested in, or risk of failure is another way these are commonly used. And they can be empirical, which means I just do a bunch of experiments. I don't have the chemistry knowledge or the physics knowledge to fully describe what's going on, but I make a pretty clean observation that if I raise the temperature, the time to failure goes down dramatically. And that was Arrhenius equation is one of those that comes to mind when you think about that. Now, Arrhenius is deterministic. It talks about the actual chemical reaction, right? And if you know the activation energy for that reaction, you've got a pretty solid connection. Now, unfortunately, many times we have so many other things going on and so many other types of interactions and reactions going on that we end up not being able to fully understand what's going on at the molecular level, for example. And so we make larger sets of observations and put it into a formula that describes that pattern or that behavior. Both are fine. They're just different levels of reflection of how well we understand it. And again, neither is right or wrong. It's a different set of tools. That's really what I'm looking at here. Okay? So the fundamental, whether we're doing deterministic or empirical, whether we're using a very simple tool or a very complex tool, we're talking about mechanisms, not failure modes, not the symptoms that the customer will see. Right? Earlier today, I'm getting, can't find that server on my browser. Let me check to see if the internet's up. And I pulled up airport utilities, and the internal network in the home is doing just fine, but the cable modem was red. And so grabbed my phone, looked up outages in our area, and lo and behold, they knew about it and they're working on it. So a quick set of root cause found that our internet access was down. Now, hopefully, on the other end of the spectrum here, the folks in the cable company are actually looking at, well, what happened? It could be a tree came down, or something got water in it and got damaged, something shorted out, whatever. And part of that failure then informs future designs, future systems, all those kinds of things. Now, one can only hope that that's going on. Much more likely if somebody came out and swapped out a part and got the system back up and running, and may or may not have done the rest of the due diligence. But when we're talking about physics of failure, it's not always physics, right? It could be chemistry, it could be software, it could be some interaction of various levels of systems. But what we're looking for is the mechanism, the underlying fundamental, I keep using fundamental, but it's the base element that then alters the behavior of our system, right? We can treat modes all day long, but if we treat the mechanism, we can actually solve it, right? Now, what confuses this is that some mechanisms show up as a wide array of different symptoms or failure modes, and sometimes there's many possible mechanisms to create the same symptom. So the cable being internet access could have been caused by thousands of different things that could have gone wrong. My modem could have failed, the cable could have failed, the interconnects could have failed, the service through the local cabling system in the neighborhood could have failed. Switching systems could have failed back at the source. There could have been failures there. And each of those elements could have hundreds, if not thousands, of different ways they could actually cease to work, cease to function well. They could be just a complete open circuit, or they could be a noisy circuit and create a degradation of the signal, and then we lose it also, and so on. The mode was, hey, we don't have a connection, no green light on my network connection, and that's a symptom. And we're not talking about symptoms here today. Now, they do get involved back and forth all the time. All right, so we use models, all right? And just like using any tool in your shop, it's pick the right tool for the job. Now, some people, when they need to separate a length of wood off of a board, right, they want to cut it an 8-foot fence board and they want to make it 6 feet long. You could use a skill saw, you could use a router, you could use a hand saw, and in hand saws you could use a rip saw or a crosscut saw. You could use a hammer, I guess, if you were really, really patient and didn't care about the edge that you got done at the end of the exercise. Yet we're probably going to use a crosscut saw or a circular saw of some sort. Skill saw might even work. And sometimes it's what's available, right? I'm not going to go buy a specially crosscut hand saw just to cut one board. I'm going to use what I have. If I was going to do that for a living and have weeks and weeks of cutting, I would get the right tool for that specific job. It's the same with physics of failure, right? Part of picking the tool is well, what question are you trying to answer? What element are you trying to understand? Is it for a design trade-off, say this thermal modeling part? Do I need to add thermal, some way to dissipate more heat, right? And so I could just use some thermocouples and measure some prototype boards I have. Now the prototypes won't be exact, the enclosures won't be exact, we won't be dissipating the same amount of heat, yet early on that might be, I already have the thermocouples and I got 2 mock-up boards here and I need to make some quick measurements. And it may inform me enough to go forward. Other times I could use the simulation tool if I have that available, right? And model those 2 circuit solutions I'm looking at and make a comparison. Other times I could use a handheld thermal imaging device of some sort, or just a thermal image of the board and see what's going on there, make some rough measurements. So if it's good enough information for me to make an informed decision, it's probably a good enough tool, right? If I walk by and I just put my hand over it and go, that feels warmer than the other one, that may not be enough information to know if I need to add another set of complexity like thermal dissipation to a board. And so pick the tools, including within physics of failure, to the level that helps you answer a question. So it could be a simple guideline like 1 watt per square inch on a circuit board, or it could be we need to do some thermal modeling here and get the appropriate tools and techniques and analysis done, right? The other way people use physics of failure is to avoid doing much more costly and oftentimes more error-prone accelerated testing. So if I've got a really good thermal modeling tool, I can take a circuit board and its dimensions, the components, and its power distribution, and really get a good image that maps to what I would actually see with the thermal imaging device if I actually built it. And we can look for hot spots, or we can look at thermal cycling effects and so on. I don't have to build a bunch of these boards and spend 6 months thermal cycling them or heating them up for 1,000 hours to see how they age. If I know how those components age, and I know the temperature, and I can get to those through modeling, I can skip doing the long, drawn-out accelerated life test, right? And so but you need to trust the model that is going to give you good information, and you need to have good information to populate the model, right? If I don't know what components I'm going to put on the board or what power loads it's going to experience, I probably am not going to have a very good model to anticipate how much heat it's going to create. The more information I have from dimensions and structures and material science and so on, the more complex of a model I can actually use. And it's good for all kinds of stuff. So let me take a look at a question. Let me leave this question out there for you and for the chat. Is what else is a good use of physics of failure? I know I didn't touch them all. So Carl's asking, how does this relate to actuarial or statistical risk analysis? It oftentimes when I hear actuarial or risk analysis or actual whatever, looking at actual failures over time and modeling that is I'm often there modeling the symptoms, and in better analysis and with better root cause analysis going on, I can get to more mechanisms. That information can help us build physics of failure models. It takes some work, but it can be done. It gives us a model of how it behaves in the field. Oftentimes it generates more questions than answers. The statistical part of this is really based on, well, how much variability are we seeing, right? And so a physics of failure model almost always has to touch on dealing with the variability. And so almost all materials, think of the overmolded epoxy that we put on electronics components, those are filled with flame retardants and a variety of other materials and epoxy holding it all together. The actual thickness will vary, the material composition will vary, the exact amount of flame retardant will vary, and so on. And so it's that variability that makes deterministic models much more difficult. Now, some of those variables really don't matter on whether it's going to function as it should or not, do the heat dissipation as it should or not, while other variables matter dramatically. And so part of building a physics of failure model and applying it is, are the variables that are included in the model, one, are they available? Can you get that information in an economical way? And two, does it actually relate to and influence the results of what you're looking for? So if I'm modeling something for time to failure information, and the thickness of the overmolding really doesn't matter on how it performs over time, I don't really need to use that information. And so it goes back and forth. If it's a variable like that, we'll use tools and statistics to talk about min and max or averages or distributions and a variety of other ways to incorporate those within these models. The key part is which ones actually have an influence on the results that we're trying to model. All right. So here's a question for you, and for those, I know there's a number of folks on the line that are very experienced. How do you explain what is physics of failure to your colleagues? Or do you even try? I could add that to it. How do you deal with that with folks? Do you start with that it started in the 50s or in the late 40s, early 50s, as the military was experiencing failures and they were trying to understand those mechanisms and building models and creating formulas and doing all that, and then the history of it? Or do you explain it as a throwback to their chemistry class in the Arrhenius equation? How do you explain what is physics of failure to somebody? Because that's not a common term across engineering disciplines. It's common in our world, but not everywhere. Right. There's somebody, a couple people are typing. Good. Gives me a chance to get a sip of water. Oh, sorry, John. Yeah, the question is how do you explain physics of failure to your colleagues, those in other disciplines of engineering? So hopefully my internet's still working. That would be a good thing. In terms of device physics, I ran into something yesterday when I was looking for some information on this, that the IRPS, International Reliability Physics Symposium, which is a very long-running conference or symposium, actually started as a physics of failure conference in the 50s, early 60s. Compare it to finite element and computational fluid dynamic models, simulation stuff. People are familiar with those, and it fits into that. Yeah, there's all these great tools that are built into our modeling and design tools, like our CAD, mechanical engineering CAD tools, has built-in finite element analysis. Oftentimes, though, engineers don't take it to the next level, saying, well, how does that stress concentration manifest as a weakness or a failure? Right? How do we estimate the time to failure? What happens if we age our materials and change their material properties and then run the simulations? I often get this deer in the headlight look at me. Like, no, everything's perfect, everything's fine. Yeah, you try to relate it to what they already know. And we do a lot of this kind of work already. And it's a model, right? It allows us to translate what we know and understand or expect into a time to failure estimate many times. There you go. I like yours, James. Stress-driven damage accumulation of materials. Yeah. Of course, that'll work. That'll be meaningless to a software engineer, but I get the idea. All right. So where do you find these models? One of them is just do a literature search. Right. Look for. Let's say you're working with a particular alloy of steel, and you're looking at its rate of rust, and the type of damage you're interested in is that if it takes the dimension of the structural steel down to a certain point, you have a failure. So how long will that take? Well, there's probably somebody that has analyzed that. There's probably somebody who's written papers on it. It's amazing the amount of studies and research that's done on different types of materials and adhesives and all kinds of different polymers and so on. There's a wealth of published data on those things. Hard time. It's often not trivial to find it, though. And so starting with your vendors and working back into the fundamental research for those material properties is a good place to start. There's tons of stuff out there, and a little bit of work, you can probably find what you're looking for. If not, then you have the opportunity to publish something unique. WARP, and I forgot to put the website on here, and I have no idea what WARP stands for. If anybody finds that, let me know. But it's at the RIAC I want to say .com, it might be .org. But if you look for, I don't know what the RIAC, and it used to be RAC, the Reliability Activity Center or Action Center or whatever they called it. It's got renamed a dozen different times. But if you search for RIAC and WARP, you'll find a database, essentially, that lists a curated list of technical papers on a wide range of different kinds of materials and electronic components. So if you're looking for models that deal with electromigration, for example, on different kinds of traces inside of electronics, you'll probably find 4 or 5 different papers on that with their associated formulas and this underpinning studies for it. So it's a great place to start if you're looking, especially electronics. They're pretty well covered under electronics and different metals, lots of steels and medical grade steels and stainless steels and stuff like that. But it's a, oops, I should actually hit enter so you can see what I type. RIAC and WARP is a nicely curated listing of what they deem is a physics of failure model. And usually they go into pretty fundamental models and reporting out on studies and backup research that supports those models being valid. So it's a pretty good vetting tool to look for stuff like that. And then another spot is the University of Maryland in the CALS, which is and I have no idea what that stands for. I think it's Life Cycle Engineering is the LCE. But they have, under the guidance of Michael Peck, Dr. Michael Peck, and many others over the years, have had the advantage of having graduate students take on a wide range of topics. There you go, Center for Advanced Life Cycle Engineering. Thanks, Ed. And they have published dozens, if not hundreds, of different physics of failure models. And they have some software available. I think it's called CALS PWA or PWB or something like that. Or it's not a real sexy name, but it's a computer software package that you feed in your bill of material and computer and circuit layout and a handful of other things. And it's billed as a way to get an estimate of the time to failure for your circuit board as it's designed without having to do an accelerated life test. Now it covers dozens, if not more, different specific failure mechanisms, solder joints and vias and thermal and corrosion and a whole range of different things. And I see James is typing, and I am going to mention DFR Solutions. Oh, thanks, James. Sarah, I'm thinking of James McLeish, who I know had joined or signed on, registered for the conference. I don't know if he's attending or not. But DFR Solutions, Craig Hillman started this company some years ago, and he came from CALS in their labs and having done a lot of the experimental work and working with clients and grad students to build models. So he has a fundamental understanding of physics of failure and modeling and what it takes to do it. And they built a software package called Sherlock, and they market it. It's got a lot of different failure mechanisms included. Again, aimed primarily at circuit boards. Is where a lot of that work comes from. Yet the same basic principles are there and can be used for all kinds of stuff. Yeah, and it can be used to predict, just as you're looking for, said, these tools, both the ones at CALS and at DFR Solutions, and there may be others I'm not aware of, that you can take a circuit board, the board with its components on it, and how it's mounted, in what environment it's in, what kind of vibration or thermal cyclings or thermal stresses it's going to see, and it can help you model what's the expected chance of failure over a year, over 5 years or 10 years, or whatever elements you're interested in. And it'll look at things like the damage to silicon active components, to wire bonds, to cathode anode filament growth within the circuit board itself, solder joint damage due to thermal cycling or bending, different heat gradients, and so on. They use a range of different simulation tools to populate the models that then go after, like I said, dozens of different common failure mechanisms for circuit boards. Now, both these models, both the CALS models and the Sherlock model tools, and many physics of failure models, don't go after, oh, somebody damaged the circuit board during manufacturing, or somebody bent it and cracked parts as they installed it. It doesn't tend to go after modeling early failures, right? The stuff that are mistakes or errors or damaged in the assembly and transport process don't always get covered. Now, there are some tools that go after modeling the transportation environment's amount of damage to systems, and there's unique failure mechanisms in some cases there, or with very stressful conditions can really accelerate a range of failure mechanisms, and some models are fit for that. But do the literature search, go to WARP, which probably I should have put first because it's a good starting point. And then if you're dealing with electronics primarily, and I know these tools can be used in a variety of different ways, CALS and DFR Solutions have nice comprehensive models to go after doing those things. But they're pretty complex and need a lot of information to make those work. And depending on what you're trying to do, they may or may not be the right solution. And I do recommend them when it's the right tool for what you're doing. Okay. So do you have a favorite mechanism that you're looking for? Oh, excellent. The new ISO standard in road vehicle functional safety is recognizing using physics of failure. It's about time. Hopefully they don't recognize parts count prediction, but that's the subject for another whole discussion. So what's your favorite failure mechanism? Is my favorite, just on the beauty of them when they show up, is the dendritic growth. You get these beautiful tree-like filament structures growing between two traces on a circuit board, and oftentimes they have all kinds of beautiful colors depending on what metals are involved with it. I like those because they make great photos. My next favorite is white powder on board, where you have a ionic contamination, only because of the story I tell about finding squalene on a board. And I'll leave that for another discussion. Right. There are lots and lots of favorite mechanisms out there. And if I model my circuit board for solder joint fatigue, and I do a detailed analysis, I get all of the physical properties of my solder joints, and I know all these great details, and I go into and do a model of it, and it says it's going to last 30 years with low chance of failure, and that's all great. But if it's overheated and I'm just burning out traces, I've completely missed what's going to cause my circuit board to fail. And so you can pick your favorite mechanisms and model them to great details, but make sure that they're relevant for what's at risk with your solution, with your product. And the hardest part is those mechanisms that are creative engineers, design and development engineers, cobble together, and we end up with a new mechanism, something fundamental that hasn't really occurred elsewhere. And so those kinds don't have models for us. We can't anticipate those. So physics of failure and modeling and these different software packages are great to what they do, but they can't predict how your product's going to fail because the supplier doesn't do something correct, or that there's a damaging step in your process that crushes, say, a component, and it gets through out to customers. It's got limits, but where they're useful, they are useful. Kind of redundant there, I guess. Right. You can create your own models, right? So it's just like let's say we want to estimate time to failure, and the first step really is, well, what stresses actually cause the failure to show up, the underlying mechanism to appear, right? And so years ago, I was working with Hewlett-Packard, and we were doing we called it off-axis ink, where we had an ink reservoir and then a pipe or a tube that would feed where the print nozzle was. And that tube was a polymer, and it had a air oxygen could diffuse through it, and it would accumulate within the tube. And if it did enough of that, you get this little bubble in there that would block the flow of ink. And so that would be a problem. And so what we wanted to do is size that tubing correctly so that it didn't diffuse oxygen so fast that it would create these blockages within the flow of the ink. And because there was a phenomena where if you were running the ink, it would flush out the oxygen at a certain level. So a small amount of diffusion was okay, given it some minimal amount of use of that device. If you let it sit too long, then it'll diffuse in there and it'll be a problem. So the question that we got was, what are the parameters that affect that diffusion rate? Well, part of it is, well, what material are we using? So we had an array of different polymers to make this tubing from that had different diffusion rates. And some of them we determined experimentally, some we got from the vendors, and some we did both. Others was the thickness, right? If you've got more to move through, it takes longer to move through it. And so changing the thickness was a major factor of it. Temperature was another variable. Air pressure was another variable. Altitude actually had an influence on it, on the air density, a little bit different than air pressure. And I think there was like 5 or 6 different variables that influenced how rapidly oxygen, which was our culprit, would diffuse through these materials. And so we created a whole series of models based on the test data we had, and allowed us to compare it against different usage rates and different other parameters that we were interested in to see which one would actually be best. Being cautious and given the risk that we were facing, we then took those top couple solutions and ran longer term testing to find out how accurate they were. And it turned out they were pretty close. So even just the modeling work we did, and to a large extent, it was back of the envelope type stuff. What are the factors that influence this? What do we know and don't know about this? Let's put it together in a model, and let's go sort out if that's valid or not. And we did all those steps. And then over time, what this team did with this tubing is then refined that sets of models so that it could look at other types of polymers, so that it could look at different kinds of conditions that led to those failures to occur. And so at the end of the day, they ended up with a very comprehensive model that allowed them to be very flexible for future designs. But it was based on trying to answer, well, how thick do we need to make this? And what polymer do we need to use? And we probably would have done that set of experiments initially, but it was always with an idea of creating a model because we knew we were going to need to do this again and again. If you're running an experiment and you know it's just only one time you need to do it, you may not set it up to create a mathematical model, which typically means you need more data points, you need more stress levels, you need more information. If I'm just comparing vendor A to vendor B, I can put it at high stress between the two of them and see which one wins. If I'm creating a model for it, I need to be a little bit more thoughtful of how I run the experiments or how I do the analysis. And so conceptually, it's an experiment. And we're collecting enough data to do a mathematical representation of the behavior we're seeing. Right? It's a research project. There's no bones about it. Right? It's not quick and dirty. It's not a gut check. We got to do the details here. Now, if you're going to do a deep dive on this thing, you could go back to school. Go to University of Maryland at KELS, for example, and other programs offer this service also, is if you had a question about how do hard drives fail, how can I model that? You could go get your master's or PhD on it and answer that question by creating a model that's a physics of failure model for it, right? You get the equipment, you get the guidance, you get all this other support. Also has to be done rigorously, academically rigorously, right? You may or may not get that ability within your organization. The other downside, and depending on your industry, is you may not want it published, right? So some of the best work is done behind the lab walls of companies, and they don't share it. It's a competitive advantage they're understanding. Where if you go to school, it's going to be published invariably at some point in time. All right, is it worth using a physics of failure model? And the short answer is yes, in the right circumstance, when it's the right tool. Even simple models can help, right? If they're misused, they're misapplied, they are going back to that 85-85, if Peck's equation is used for solar panels and it doesn't have a model that describes that stress to relevant failure mechanisms like delamination, it's not a terribly, that's not that it's not useful, it's just a waste of time. So try to connect these as often or as clearly as you possibly can. So let's take a look real quickly at a couple different examples of models. I'm pulling these off of some of the historical documents. This, from what I understand, this model of electromigration called Black's equation was one of the earliest descriptions of time to failure for a specific failure mechanism. I don't know whether it's the very first one or not, but it's one of the first that gets credit for being there. And it's measuring time to failure is a function of a constant, and it's primarily based on the physical dimensions of the traces. Now, these are traces in the silicon. These are those metal lines that connect the transistors within a silicon device. A transistor or a integrated circuit. Drawing a blank, had a senior moment. J is current density, and that's a function of how much current, right, and its cross-sectional area. So we're looking at density. Activation energy is dealing with the ability, and this particular activation energy has to deal with the ability of that metal to give up an atom, essentially, of that metal to release it from its lattice. And so it then is free to move with the current flow to where it shouldn't be, for example. And a few other pieces in there. The basic idea, though, is that there's a criteria for what a failure is. The trace gets narrow enough that it constricts the current flow and heats up and usually then melts or goes open. And that might be defined as what a failure is. And with enough current flow and enough energy in it, it's going to move elements of that trace usually into a hillock, it's called. I actually saw a video of this one time. It's fascinating. And eventually it thins out where it's stripping the metal off, and as it thins, it gets a higher current density, so it makes it worse, and eventually it strips out enough metal that it overheats and goes open. But it's a very simple model. There's only a couple of elements in here. If you're going to use this for accelerated testing, you can make it a ratio of time to failure in stress conditions and time to failure or at accelerated conditions and time to failure at use conditions. Then you get rid of that constant piece in there, that cross-sectional area, and it makes the formula a little bit simpler. But you still need to know the activation energy for the relevant reaction, and you still need the current density. Now, the scaling factor is often 2 in this equation from early on. Different metals may have different scaling factors, but it's a very simple model, and it may be useful for you if you're dealing with traces and electronics. Yeah, and James has got a couple of comments on there on autonomous vehicles and all, yeah, just all the electronics we got in there. It's amazing how many questions and ways things can fail now, like my cable service this morning. Here's one that's a little bit different than that Peck's equation mentioned earlier. If you take out the voltage element of this, it's not really focused on wire bond attach. It's looking at corrosion is the one that we're more commonly familiar with, is the relative humidity and the temperature elements of it, we're looking at the ability of an overmolded epoxy body to seal from corrosion. And this one, Peck, I mean, he did a lot of work on the early encapsulation of components. Added that if you have this voltage element in there, it helps you to understand wire bond attach, whether it's attached firmly or not. And this is an early model, and quite sure it's relative to a specific style of bonding and the metals involved and the processes involved. Yet it's an example of here, there's three variables involved. Well, bits of different pieces of information are needed: relative humidity, voltage, activation energy, and temperature. So a number of different things to get a model for time to failure for these wire bond attachments. And then I don't want to go too far into electronics only, and everything's not involving the activation energy and the Arrhenius equation. Is there Steinberg did a life's work on vibration. He's got some excellent books out that capture a lot of this information, and one of them was looking at the vibrations effect on solder joint reliability. And so this equation goes after the amount of displacement. There's a few more steps to get to time to failure in this, but it's looking at a range of different kinds of information. Your displacements and transmissibility, natural frequencies, power density, power spectral density, kind of waveform that this thing is seeing, and so on. And all kinds of other things, how thick it is, what kind of stiffness it has. Lots and lots of different elements get involved in sorting out vibrations effects. In this case, it's on solder joints. And so you can see there's lots and lots of different kinds of models, and this is just three of hundreds and hundreds that are available out there. And some you can do in Excel, some you're going to need some simulation tools to make it actually work. Yeah, and fatigue is a good tool. Miner's rule is a way of combining different levels of vibration. Peck doesn't tend to use, or not Peck, Steinberg doesn't tend to use Miner's rule. It gets a little bit more complex using the power spectral density type work on that. And again, it often depends on what's the failure mechanism. So that often plays a role in how complex a particular model will have to be. All right. And so, in summary, physics of failures is one of the tools in our tool bag. And within physics of failure, there are many, many, many models. And it's using the appropriate model or building the appropriate model allows you then to answer questions, to making comparisons, to estimating future failures, to evaluating risk. And so it is a group of very, very useful tools that allow us to understand the world about us and inform decisions so that we can make better and better or reliable products. So let me pull over the final slide so you have where the downloads are and a few other bits in there. And so that's today's presentation.